Welcome back. In this lecture, we're going to start talking about random variables. So what we've seen so far are three of the key components to sort of a mathematical treatment of probability theory. So we've seen sample spaces, and these contain the sort of outcomes of your random process. We've seen sigma algebras, and these are sort of the events that you want to assign probabilities to. And we've also seen, probability measures, and these assign probabilities to your events. Okay, and the last thing that we need is random variables. Okay, and what is a random variable? Well, let's just talk about it roughly for a bit. So if you've got some random thing, say you're rolling a dice, say you're rolling 10 dice, well, an example of a random variable would be something that you compute based on the rolls of your dice. Say you could have the total sum of dice. Okay? Alternatively, if you were randomly sampling from a collection of people and you assign to each person a real number or a positive non-negative real number which represents their height, that could be another example of a random variable. Okay, and it basically is a function which takes some random stuff going on and gives you something else out of it. Okay, but as we've seen, if you're outside of sort of the finite or countable sample spaces, we have this sigma algebra thing going on, which is sort of, you have to be careful that you remain within your sigma algebra if you ever want to assign probabilities to things. So for this sake, we're going to define random variables with respect to sigma algebras. Okay, so let's get into the definition. Okay, so we'll have an omega, an f, and omega dash f dash be event spaces, or measurable spaces, depending on which term you prefer. Okay. Random variable x from omega to omega dash is a function, and as I mentioned, we need to take into consideration sigma algebras such that this set x in a dash, which is defined to be the preimage of a dash, which alternatively you can see it as the set of omega dash in omega, omega in omega such that x of omega is in a dash. So these are all different notations for the same thing, and you want each of these sets to be in your sigma algebra for all a dash in f dash. Okay? Now what this is saying is that, if you want to know, if you look at the set of outcomes such that x is in some set you can assign a probability to in your codomain, then you should be able to assign a probability to this set in your domain. Okay, and this is really going to allow us to be rigorous and careful with random variables rather than just defining them as sort of a function which is random. Okay, and so as we saw in the video on Lebesgue measure and Lebesgue integration, this looks fairly similar to the definition that I gave of a measurable function. In that case, you take your codomain to be R with the Borel sigma algebra, and we can check that the definition of a random variable contains the definition of a measurable function with this as a special case. Okay. So let's get into some examples. Okay, if F is the full power set, then every x from omega to omega dash is a random variable. Regardless of what omega dash and f dash are. Now, why is this? Well, we check x in a dash. Well, this is a subset of omega, and so therefore it's an element of the power set of omega, which is f in this case. And this is for all a subsets of omega dash, and therefore especially it holds for all a dash in f dash. And therefore we find that x is a random variable. Okay, so note that in this case our codomain has this discrete sigma algebra, and therefore you're not really having any restrictions in this case. Okay. Alternatively, we get some other sort of simple, sort of trivial examples like this one. So if instead we take f dash to be the indiscrete sigma algebra, any x from omega to omega dash is a random variable. Regardless of omega and f. And why is this? Well, x in a dash, well, we've only got two choices for a dash here, right? It's either the empty set or omega. So this is either going to be the set x in the empty set or x in omega dash. Oh, sorry, this should be a dash here. Okay, and this is if a dash is the empty set, if a dash is all of omega dash. Okay, and well, what are these? This is just the empty set, and this is just omega. Okay, and in either case, these are in F, regardless of what F is. We've seen that any sigma algebra always contains the empty set and the full set. Okay, so yes, any x here is a random variable if you put the codomain with this sigma algebra. Okay, and so for those of you who have seen some topology, this should make sense. You're either giving your domain the topology that makes everything continuous, or your codomain the topology that makes everything continuous. And this is sort of the measure theoretic version of that. Okay, so now we have some examples that mess things up in the other direction. And after this example, we'll just end this part of the lecture. Okay, so if x from omega to r, right. If x from omega to r is a map from, well, this event space to R with, oh, sorry, that's a R with the Borel sigma algebra. And what we give F the we give omega the indiscrete sigma algebra, empty set omega. Then x is a random variable if and only if x is constant. Okay, and how do we see this? Well, yeah, so for each R in R, we can ask, well, what is the set X in R? This will sometimes denote as X equals R for the obvious reasons. Well, this has to either be the empty set or the full set if X is a random variable. Okay, so let's say we assume X is a random variable. Then for all R in R, this set must be either empty or the full space, because we know as it must be an element of F, which is the empty set and all of omega. Okay, well, if X, there must be some R such that it's the full space, because you can't have a function which is not equal to anything anywhere. That would be the case if everywhere were the empty, if every R corresponded to the empty set. Alternatively, it can't be the full set for more than one R. So there exists a unique R in R such that X equals R is omega, and well, this exactly means that X is constant. Constantly equal to R. Okay. Alternatively, if X is constantly equal to R for some fixed R, then you just go through this procedure and you find that for any R dash which is not equal to R, you get the empty set here, otherwise you get the full set, and therefore it's a random variable. Okay? So in this case we don't have many random variables. Well, yeah, we've only got sort of a one-dimensional vector space of random variables. Okay, and moreover, this example, it doesn't really require that this is the real numbers with the Borel sigma algebra. You can replace R with the Borel sigma algebra as the codomain with other measures, with other event spaces, and providing your sigma algebra is fine enough, you'll find exactly this same reasoning follows through. I would recommend you have a think about this and check which property of R with the Borel sigma algebra we're using here. And yeah, just have a go of that as an exercise, and we'll keep going with this with some more properties of random variables in the next lecture.